morning, everybody. So I am Sayantan Nandi, and today we are going to talk about Intro to Convolutional Neural Networks. In our lecture today, we are going to talk about how CNNs work, how they work, and basically what they do. So first of all, let me give you a very brief introduction in what are CNNs. So basically, CNNs are AI models. Basically, they help us to do image-related stuff, like for the stuff that ChatGPT does. Like for example, if you like post a image into ChatGPT and tell it to identify all the objects in that image, then that's what the role of CNN comes in. So that's where CNN plays a very important role. So basically, if there's any sort of task related to image recognition, image classification, sort of any task like that related to any visual stuff, CNNs are the things which help us the most. So basically, just to give you a very basic understanding into a very basic analogy, let's say you have a AI network which can basically play any sort of game, let's say, and let's say the first prototype that you build of that game, you don't use CNN. So because you're not using CNN, the AI is missing out on a lot of potential to be much better. Like, let me give you example of how it's more beneficial to use say CNN than the basic AI network. Basically, in the basic AI network, all the training data that is fed into that network is just the dimensions of where the AI is situated right now. But if CNNs come into the play, then the whole game changes. Basically, uh, the AI can now have eyes of its own. He can see what's going on around in his environment, and from that he can train itself very much better than just from dimensions. So that's a very basic analogy I can give you. CNNs are basically AI agents with eyes. So uh, basically, if you talk about CNN, there are a lot of processes in that, but broadly speaking, the first one is basically convolutional operation. Then we have the ReLU operation, or simply linearity of operation, and then we have the pooling operation, and then at last we have the flattening operation. So those are the four operations that we have in the process of image recognition via CNN. So first of all, let's talk about the basic layout of CNNs. So if we see in this diagram, we can see that there is input image that you give to the CNN. Then it basically does its job in recognizing it, classifying it, and then there's basically output label on the image class. Basically, if let's say I train the CNN to recognize whether the input image is a dog or a cat, then the output label, let's say I'm putting in a picture of a dog. So the output label will be dog. If I put a image of a cat, then the output label will be cat. So that's how basically CNN works. So let's for example say that we want to build an application in which we want the CNN to recognize what kind of emotional situation we are now right now in. So if let's say I'm post a image of myself smiling into that CNN, so it should say that I'm happy. But if let's say I'm posting an image of frowning, then the CNN should basically output that I'm sad. So let's just say that we want to build something like this, a basic emotion detector. So, before diving into what all this is, before all that, let me clarify one thing for you. CNN does not process the image as we humans do. A CNN basically process the image in a much more complicated way. It converts that image into a sort of matrix, the matrix that you have seen in your maths and physics and all. So that CNN converts that image into matrix, and to give you a gist of how it is done, I've included this example. So let's say I put in a photo of myself smiling. So it would look something like this on the very left hand. And let's say I want to represent it in the form of a square boxes kind of thing in the middle image, as you can see. So it would look something like in the middle one. So right now, let's say I want to represent it with in numeric terms and basically convert it into a matrix. And let's say I want to represent the black spots as one and the blank white spots as zero. So the basic matrix that will be formed from the middle one will look something like this. Like you see this one, this black box has been converted into a one. Then this has converted into a one. Like these three have converted into one. This black box once again one, and these two also ones, and the rest of them are zeros. So this is a very basic and very far-fetched example of how CNNs basically perceive any sort of image in their input. this is exactly not how the CNNs work with the images, but this is a very basic analogy of how it's done. So basically, let's say we want to know how it's actually done. Let's say now I want to give you a very formal kind of introduction to how it actually perceives the images. So basically, what it does is that let's say you see this image. So this image is made up of maybe hundreds of pixels or maybe thousands of pixels. Computer screen on which you're probably watching this, or a mobile phone, is made of millions of thousands and thousands of pixels. So what are pixels? Pixels are basically small boxes, and if you stack them up together, you have a screen sort of image, if you can say. So the image right here, it can be converted into lots of smaller boxes, and those smaller boxes are known as pixels. Like you must have seen in your desktop or in your phone, there must be the size of the image mentioned. For example, the videos that you watch on Instagram, they're mostly 1920 into 1080. So that basically is the length and the width of that image. And what that represents is not 1920 in 1920 length in centimeter or something. That's basically 1920 pixels and 1080 pixels. So that's how pixels are can be explained. So basically, the CNN perceives the images in form of pixels. So each pixel of that, uh, basically each pixel of that image is converted into a very a value in the matrix. And let's say we take an example of, let's say, this black and white image. Let's say it's a 2 by 2 pixel image. So there's just 2 into 2, 4 pixels. This is pixel 1, 2, 3, and 4. So this is a 2D array. And let's say we want to see how the CNN perceives this. Of course, this might not be the actual way the CNN perceives this, but is uh, very near to how it actually does it. So this is a black and white picture. So the pixels might be just made up of black and white spots. So how the basically the CNN perceives this is basically this will be converted into a matrix of 2 by 2, 2 rows and 2 columns. So basically, basically each element would correspond to the amount of color in that pixel. Let's say in this pixel, there's this pixel. Let's say I'm just assuming this pixel is fully black. So this might be, let's say I'm denoting this as 1. All right, because this has 100% black color. And let's say this is somewhat grayish. Uh, that's basically, I'm just assuming half black, something like that. So this might be zero point 0.5 when it's actually converted into a uh, matrix, the matrix that's the CNN basically perceives. So I'm just taking this example as ones and zeros, but this values actually lies between 0 to 255, and that's just how the black and white images will be processed by the CNN. But let's say there's a colored image. So for that, there's layers of the same matrix. So one matrix might be containing the values of the blue in each pixel. Another matrix might be containing the value of green in each pixel. Another matrix, the one which you see at the here, it's basically it contains the red in each pixel. So that's how the CNN perceives the images in form of matrices. All right. So now I'm going to show you a video of how the basically the first step occurs in the convolution operation. That's basically the convolution process, convolution operation process. So basically we have till now we have learned how the image is converted into a matrix. So now let's learn how that matrix is operated on, and basically how the CNN works throughout the process. So let's say this is the input image. I'm getting this as an uh, matrix. This is basically what the CNN perceives. So basically, the convolution operation, what it does is that we take a feature detector. A feature detector is basically a matrix, and it could contain random values according to what the requirement of that feature is. The feature might be black spots, the feature might be edges, the feature might be blur, or them. There are a lot of feature detectors that are used in these CNN convolution operation. So what happens is that basically this feature detector is mapped on the input image matrix, and we see that how many boxes or how many elements are matching with the feature detector. So for, let's say, the first example over here, there's zero, and there's 0 and 1, so it's not matching. There's 1 here, but it's not over here, so it's not matching. There's one over here, but it's not over here, so it's not matching. There's two ones over here, but it's not here, so it's not matching. So the total number of matches is zero. So why we write over here zero. And the matrix which forms by doing this is basically the feature map. The feature map basically tells about the various features of the image. Just like I said, blur, edges, black spots, various features that are basically that basically helps a CNN to learn more about that image. And so let's play this video to basically show you how it's done. So first of all, it's done for this one. So you see it's zero over here, but then it moves on to the other values also. And see over here, you can see this. And like so, if I just move to the end, so basically this is how the feature maps are formed. And there's just one feature map formed. Just like I said, there are maybe hundreds, or there's not a fixed number, uh, but there are a lot of feature maps depending on how many features you want to detect in the image. So that's basically how the convolution layers are formed. So just to give you a brief overview, this is what it looks like. So basically, this is the input image. Uh, the features are mapped into these feature maps, and then basically a lot of convolution layers are formed. And so then the next operations are applied on these, and then so on. It happens like that. All right. So before going on to the what happens after this, I want to explain to you a concept known as spatial invariance. So what is spatial invariance? Spatial invariance is basically the ability to recognize any sort of object in any sort of image, irrespective of its position in any of the images. So what it means basically is that let's say I'm building a CNN which basically recognizes what type of animal there is in the image. So this is a leopard. So let's say I want the CNN to recognize the leopard in this image also, in this image, in this image, in this image, in this image also, all of the images. But if you see one thing, the leopard over here is situated somewhat in the right corner. Uh, his face is not clearly visible from the other end. If you see here, his body is more visible, but his face is not that visible. If you see here, his position is kind of different. If you see here, the it's not that very clear of whose face is that. But if you see here, his face is very clear, but his body is not sure. If you see here, there's another position in which the leopard is. So basically, we want the CNN to recognize that this is a leopard, irrespective of where it is situated in the image. So this is basically known as spatial invariance. So what helps us to do this in a CNN? That's basically pooling. And in this video, we are going to talk about max pooling. So basically, pooling helps us to do this spatial invariance in the CNN. So basically, what pooling does is that it compresses the images, the convolutional layers by a very high extent, and it also preserves the main features of that image. It basically compresses the image, but without actually harming the main features of that image. So there are a lot of pooling techniques. There is some pooling, max pooling, another sort of pooling techniques. But today we are going to talk about max pooling. So basically, what max pooling does is that let's just start the video. So basically, what it does is that it could be 2 by 2 or 3 by 3. It depends on the user, uh, how big the map he wants to take. Like if you want to talk about the AlexNet, uh, which was built by the founders of OpenAI. So they used a 3 by 3 matrix. But let's just, for the sake of easier understanding, we are using a 2 by 2 matrix. So what basically max pooling does is it's very simple. It's there in the name. Sorry, it's there in the name only. So basically, what it does is that it takes the max value of that particular matrix. So in this, the max value is one. So we keep it as one. Then we move on. There's one over here. Then we move on. 0. Then if we go over here, it's 4. If you see. So there's this, if we see it's 4, then this 2. So it does this to the whole feature map. You must be knowing what the feature map is. We just talked about it just a few minutes back. So basically, this is the pooled feature map. So let me give you an example of how this basically minimizes, ensures spatial invariance. So basically, see, let's say this 4 number, let's say it denotes some kind of feature. So it in this image, it could be, let's say in this feature map, it's situated over here. But in some other feature map, it could be situated over here. All right. In some other maps, it could be over here. In some other maps, it could be here. But what max pooling helps us to do is that we can extract that number 4, element 4, no matter where that 4 is situated in that whole matrix. So it doesn't matter where that 4 is. We can extract it no matter its position. So that's basically what I was talking to you about spatial invariance. So that's how CNNs recognize features no matter where they are situated in an image. All right. So then the last step is basically flattening. So this is the pooled feature map we got, and flattening is basically converting this into a single row matrix. All right. So this is the pooled feature map we got. So we just flatten it. Just like the name suggests, it's just flattening. So we take the pooled feature map and we just flatten it. So we get this single row matrix. And what this helps us to do is that we can basically input these values into the uh, input layer of a artificial neural network. And then it could be used to train that AI agent. All right. So basically, that's how the process is done in of basically how CNNs basically recognize images and stuff. All right. So just to give you a summary before moving on to the example, I'm just going to give you a summary of what happened here. So basically, this is the image, and then we do the convolutional operation and form the convolutional layers. And how it's done? It's basically done using features or maybe filters, maybe filters basically, or kernels also, and they form the convolutional layers or the feature maps. And another thing which was missed in all those slides is basically a special kind of activation function is applied in these feature maps, which is the ReLU activation feature. So basically, what it does is basically it basically helps us to uh, minimize linearity in the neural network, because linearity is not good for a neural network. So let's say there's linearity in our neural network. So that means there is a linear relation between the uh, variables in the neural network. So what all structures or graphs can we draw in a piece of graphs? It could be a straight line or something like that only. But if let's say the relation between those variables is not linear, it's exponential or something like that. So then we can draw a circle, then we can draw a parabola, we can draw all sorts of ellipse and every sort of structure that you can imagine. So that basically helps us to derive more complex relations between all those variables in the neural network. So it basically helps in training the network. So that's why we use the ReLU function. And then we go on to the pooling layer, as explained it. So if you see, this is a much bigger input image. It's converted to a much smaller, and then after pooling, it's much smaller. And let me just and after this, the flattening process is of course done. But let me just tell you one thing. This process is not done just once. It depends on what kind of AI network you're building. But this is not done once for any kind of network. This is just done for the teaching purposes. And so after flattening, you can see the values from the flattening layer can be put into this input layer. And then basically the whole neural network is trained. And then basically we get the output. So let's say the input image is a dog. So it's basically first the convolution occurs, then the ReLU function is activated, then the pooling is done, then the flattening is done, then the whole neural network is trained. Then there might be some uh, uh, retraining that will be done. And after a lot of training, the outputs will be displayed, and there will be, let's say, just two outputs, uh, a dog or a cat. So let's say the chances of that image being a dog is 95%, and the chances of being a cat is just 5%. So that's how the whole CNN works, uh, and that's how it recognizes images. So just to give you a very practical example, so this is a tool built by a scientist, by an AI scientist. You can check it out. I'll provide you the link if you want. So basically, it shows you in a very practical way how CNN networks work. So if you see, I draw this 4 over here. So this is the input image. This is the input image basically, and it's converted into a matrix, as you can see. It's divided into pixels, and then these are the basically the feature maps. A lot of kernels of filters may be applied on this one to get all these feature maps, and then the pooling must have been done in this process. Or once again, there might be the feature maps. These might be once again the feature maps. Uh, basically, the feature maps are not formed once. the filters are mapped on those convolutional layers a lot of time in the layer. So after you see this, basically up till this process, it makes a sense. But from this step onwards, it doesn't make sense to the human eyes, but it of course makes sense to the CNN. And then if you see, this is the basically the flattened layer, and then is basically fed into the input layer of the artificial neural network, and then basically and then basically this is the output we get, and that's 4. All right, so that's basically a very practical example of how CNNs work, and that's it for this tutorial. So that's how CNNs work. This was just a very short intro to how CNNs work. Go and explore more. I might try to bring some hands-on tutorial into building something real-world application of the CNN in this one. So thank you.